Hello chemists, welcome to this video where LaJoy and myself will be covering a GCSE Topic 1 atomic structure. We'll be covering key parts of this topic that will help you develop your understanding of atomic structure. And just for watching this video, we will be giving away a free lesson to help you solidify your basics. Just click the link in the description, enter your details, and we will send it over to you straight away. If you want even more help, we have My Resources for Chemistry, where myself, LaJoy and Manny have created an incredible set of notes, plus video explainers and practice questions, all for free. Yes, you heard it right, completely free, no catches. Click the link in the description, let's get cracking. Greetings GCSE chemists. In this video we're going to be talking about all things atomic structure, so enough yapping, let's get cracking. Atoms. Now, absolutely everything is made up of atoms, and atoms are the smallest part of an element that can exist in isolation. Now, if you don't know what an element is, more on that in the next slide, but the elements are arranged in something called a periodic chart or a periodic table, and voila, here is the periodic table of elements. Now, the elements in the modern-day periodic table are arranged in increasing atomic number or proton number, and the proton number is the element ID. This tells which element we're talking about. So, for example, here is a lithium. It is a lithium because it's got 3 protons. And then as we move across a row or a period, the atomic number is increasing by 1 each time. And then we get to the end of the row, is a full stop, and then we move to the next row along, the next row down, and then we can see that the atomic number, or the proton number, continues to increase by 1 each time. And there are roughly around 100 elements. This is showing 118 elements. Who knows, you guys might discover some more. So you might be thinking, well, what actually is the definition of an element? Well, that's one that we need to know. An element is a substance that contains only one type of atom. So in this little cartoon, we only have one type of atom. We've got just chlorine atoms. So this would be classed as an element. Just to reiterate, elements contain only one type of atom, in contrast to compounds, that is. And in this cartoon, we can see that in this substance, there are 2 different types of atoms. So we've got oxygen atoms and hydrogen atoms. So this would be classed as a compound. So the definition of a compound is that compounds contain 2 or more different types of atoms or elements that are chemically connected, as you can see those little sticks connecting the oxygens and the hydrogens. And in the compound, the elements are combined in fixed proportion. So we've got 2 hydrogen atoms for every 1 oxygen atom. And if we have a look at the compound in a slightly deeper context, well, the compound here, H2O, is called water. And that compound has vastly different properties from the elements that made it. So the elements that made water are hydrogen and oxygen. Well, hydrogen is a colorless, odorless explosive gas and a diatomic molecule. Oxygen, a colorless, tasteless, odorless gas at room temperature and pressure, a diatomic molecule. Whereas water, which consists of oxygen and 2 hydrogen atoms chemically connected, well, this is a tasteless, colorless, odorless liquid that we need for survival, and has a very high boiling point in contrast to hydrogen and oxygen. And this is a liquid at room temperature and pressure. So the properties of the compounds are way different to the elements that make up a compound. Very important to note. Okay, so we've done elements in compounds, and let's move on to mixtures. So an impure substance is the same thing as a mixture. And mixtures contain more than one substance, but these are not chemically combined or connected. And mixtures can be separated quite easily by physical processes. And we're going to have a look at each physical process in turn in the next couple of slides. So this is a little cartoon of a mixture. So we've got light blue substance and a dark blue substance. They're not chemically connected. So it's akin to me saying, if I just want to take the light blue one out, I can do that. Imagine this is a box full of Skittles. If I want to take out the green ones, I can do that because the Skittles are not all glued together. They're not chemically combined. So, what physical processes do we need to know? Well, we need to know about filtration. So filtration is a separation technique for separating mixtures of insoluble solids in liquid. So imagine in this beaker, I've got a mixture of sand and water. My sand is my insoluble solid and water is my liquid there. They do not dissolve. The sand is not soluble in water. And then if I wanted to get the sand and the water, what I could do is pass it through some filter paper. The sand will be left behind, call that the filtered solid residue more generally, and then the water is going to pass through the filter paper, and that can be collected in a conical flask, and that liquid that we collect is called the filtrate. Moving on to evaporation/crystallization. Now, evaporation/crystallization, this is a separation technique to separate a dissolved solute or dissolved solid from a solution. So in evaporation, imagine this is my solution, and in my solution I've got some solute or dissolved solid. And if I want to get that dissolved solid and just get the actual solid out of solution, what I do is I literally just evaporate the solution. So the solvent will evaporate/boil, and the powdered solid would be left behind. And crystallization relies on this property of evaporation/boiling, but it's slightly different. And there is a core practical or required practical that you need to know, and that is making copper sulfate crystals or making crystals. So step number 1 is we normally add a metal oxide, and this is added in excess to the acid to make sure all the acid reacts. So we're making a salt in that first process. The salt is soluble. The excess metal oxide is not. So what we do is we filter off the excess metal oxide. Once we've done that, our filtrate is now the salt solution. What we're going to do is we're going to evaporate most of the solvent to get a saturated solution. So we're not getting rid of all of the solvent. So no more solid can dissolve in that solution. And then what we do is we leave the solution to cool, and things become less soluble the colder they get. So what starts to happen is crystals form. So it's no longer powdered, it's no longer a fine powder. We should get nice big fat crystals, and then we can just isolate the crystals and dry them on some filter paper. Moving on to distillation. So this is simple distillation, by the way. So distillation is a separation technique where we use the differences in boiling points between two liquids, or the differences in boiling points between some dissolved solute or dissolved solid and the solvent. So for example, if this is salt water, this is NaCl dissolved in H2O. What we're going to do is we're going to heat the round bottom flask. And if we heat the round bottom flask, which substance is going to boil first? Well, the one with the lower boiling point. Well, water has a much lower boiling point than salt. And as you can see here, the water in the solution boils first, has a much lower boiling point than the NaCl. And what happens is the vapor travels up, it can't escape, so it goes in this direction, to the right-hand side, to a condenser, which has water running around the outside. So these walls of the condenser are cold, and then the vapor condenses when it hits the walls of the condenser. And then it trickles down, and we collect that liquid in a conical flask, which we call the distillate now. And what's going to be left behind in the round-bottom flask? We are going to get salt left behind in there. Moving on to chromatography, everyone's favourite. So chromatography is a separation technique used to separate coloured mixtures. Not strictly true, but for GCSE it works well. And let's say I've got my different mixtures over here. The different mixtures can be separated according to how attracted they are to the chromatography paper and the stationary phase. So let's say I've got dye 3, which is a mixture. So it's got multiple parts or different components, we could say. And what happens is we're going to put the dyes on some filter paper and then plonk it into a beaker, and we're going to make sure that the dyes are above the solvent level. And then as the solvent starts moving up the paper, it's going to take the different components of the coloured mixture with it. Now, how far do the components of the mixture travel? Well, this depends on how attracted they are to the chromatography paper, which we call the stationary phase, or how attracted they are to the solvent, which is called the mobile phase because it's moving, and the chromatography paper is static, therefore the stationary phase. Now, if one of the components is more attracted to the stationary phase, then it moves less far up the paper. So for example, imagine there was a spot there, hasn't moved very far up the paper, it's going to be more attracted to that component is going to be more attracted to the stationary phase or the paper. However, this spot, which has moved way further up, is not very attracted to the paper, but more attracted to the solvent or the mobile phase, which is why it gets carried up a bigger distance. And that is chromatography in a nutshell. Remember, chromatography comes up in paper 1 and can come up in paper 2 as well. So it comes up in the analysis section of paper 2. Okay, moving on to the development of the model of the atom. So, first, let's have a look at how models of the atom have changed over time. So atoms were thought to be tiny solid spheres in 1803 by John Dalton that couldn't be divided or broken down. But that model changed due to Thomson and his experiments. So I think Thomson discovered the electron around 1897, but don't quote me on that. And based on that discovery of the electron, they had to change the model of the atom. So then Thomson comes and says the atom is a diffuse, so spread out ball of positive charge, and there are negative electrons embedded within it, just like plums within a pudding. He didn't call it the plum pudding, that's what people called it. Now, more on the next part later, but then, after an experiment, we had to change Thomson's plum pudding model. And this is based on the gold foil experiment or the alpha scattering experiment. And based on that, Ernest Rutherford says that actually, I think it was actually his students who did the work or the experiment, but he says that the atom isn't really a ball of diffuse positive charge. That positive charge is concentrated at the center of an atom. And most of the mass of an atom is concentrated at the center as well. So that positive charge collapses into something small and concentrated at the center. Therefore, the negative electrons must be going around the outside. And most of the atom is empty space. And this changes sort of with the advent of quantum chemistry. And Niels Bohr comes along and calls his model, I guess, the planetary model, where the electrons are orbiting the nucleus at specific distances or energy levels. So it's a slight refinement of the nuclear model. But these are sort of the pictures we have of the model of an atom, especially I do anyway. So, let's have a look at the alpha scattering experiment in a little bit more detail. Now, if Thomson's plum pudding model was true, and they fired alpha particles, which are helium nuclei, at the gold foil, according to the plum pudding model being true, what would have happened is the alpha particles would only have been deflected slightly, but all of them would have gone through. And that's because there is a diffuse ball of positive charge and there isn't much repulsion. So all of them go through. However, what actually happened was this. Now, a lot of the alpha particles did go through. So here is my radiation source. Here is my gold foil. You can see a lot of them go through with very slight deflection. So we're on track for Thomson's model until this happens. So the alpha particles fired at the gold foil, and some deflect at such huge angles. Given the fact that some deflected at huge angles, that is saying there must be a small concentrated positive mass at the center, because when we fire this alpha particle, this helium nuclei, at this gold foil, we get large repulsion, and that must be due to the fact that there is a small concentrated positive charge at the center. So that huge repulsion means that alpha particle, or the helium nucleus, is bounce back effectively. So deflected at huge angle, so it doesn't go through. So, observation, most alpha particles pass straight through, therefore the atom is mostly empty space. Now, some deflected slightly. I would say the positive charge is concentrated in a small central area, and those that are deflected backwards massively, well, there is most of the mass and the positive charge concentrated in a tiny nucleus at the center. So most of them go through. Most of the atom is empty space. The ones that deflect back at a huge angle, most of the positive charge is concentrated at the center of the atom that we call the nucleus, and most of the mass of an atom is at the nucleus as well. So, just while we're here, quick timeline of discovery of subatomic particles. Thomson discovers the electron first. I think the proton is discovered by Rutherford. After this, they didn't actually call it the proton at this point. And then in 1934, perhaps, or 1932, Chadwick discovers the neutrons. So we need to know the timeline of subatomic particle discovery as well. So moving on to subatomic particles, the protons and neutrons are found in the nucleus. So the nucleus is the center of the atom, where we get the concentrated mass. That's where most of the mass of an atom is. So protons have a relative charge of +1. A relative mass of 1, and they're found in the nucleus. Neutrons, in this case, those red subatomic particles, they have 0 relative charge, but a relative mass of 1, also found in the nucleus. Now, whereas the electrons, which is what we're interested in chemistry, the electrons are found around the outside in energy levels or shells. Now, electrons have a relative charge of -1, and they have fractional relative mass, so way smaller than that of a proton and neutron. In fact, 1 over 1840. Very, very tiny. And these are in orbitals around the nucleus. Just while we're here, the radius of an atom, so the radius of an atom is around 10,000 times bigger than the radius of a nucleus, and we need to know how to do those calculations as well. Okay, atomic number and the mass number. So, as we saw in the periodic table, the elements are arranged in order of proton number, and the elements are given element symbols. The first letter is always a capital. The second letter, if it has a second letter, will be a lowercase. That is definitely not capital. So normally given an element symbol and two numbers either side. Usually the mass number is at the top, and the mass number is defined as the sum of the protons and the neutrons. And the smaller number, usually at the bottom, is the atomic number, which is the number of protons. That's given to us for free in the periodic table. And remember, the proton number defines which element we have. It's the proton number, because if that is 3, then the element is lithium and it can't be something else. If that proton number changes, it's a different element. Okay, let's have a look at an example. Example being boron. So A is usually the symbol for mass number, so 11 is the mass number here. So the mass number is 11. And the mass number is the sum of protons and neutrons. Just going to quickly change to a pen here. So if we have 5 protons, we don't know what the neutron number is, but we know that the sum of the protons and the neutrons must get us to the mass number of 11. So therefore, the neutron number must be 6. So what we've really done is to work out the neutron number, what you have to do is do the mass number, take the mass number, and subtract the atomic number from it to give you the number of neutrons. The proton number is given to you in the periodic table. And then the only thing that we haven't worked out, which is the electron number. So in a neutral atom, the number of protons is equal to the number of electrons. So if we have 5 protons, we have 5 electrons, and the charges cancel out. Okay, relative atomic mass. So we should know what an isotope is. An isotope is an atom of the same element. So it is the same element because we have the same proton number, but a different mass number because we have different neutron numbers. So chlorine, for example, can exist as 2 isotopes, chlorine-35 and chlorine-37. Now, if I want to work out the relative atomic mass, which is the weighted mass of all the isotopes averaged up, then what we do is we're going to multiply each value by its relative abundance. So what that means is I've got 3 chlorine-35 isotopes, multiply them together. I've got 1 chlorine-37 isotope, multiply them together. We're going to add these values to get the total mass. So the total weighted mass is 105 plus 37, which is 142. And then we're going to add the total abundance, so 3 plus 1 equals 4. We're going to divide the weighted mass by the total abundance to give us 142 over 4, which is 35.5. And that is the number that you see. It's the relative atomic mass that you see in the periodic table. Okay, and then finally, moving on to electronic structure. So, as we've said, the protons and neutrons live in the nucleus, which is concentrated at the center of an atom. And that's where all of the mass of an atom comes as well. And the electrons live in energy levels or shells. So, as we can see here, we've got 3 protons in this atom. And at the moment, we only have 2 electrons being shown that live in the shell. So, 2 electrons occupy the first shell. So, only 2 electrons occupy the first shell. And we need to know the order of electron filling. So, 2 electrons, maximum of 2 electrons in the first shell. 8 electrons in the second, 8 in the third, and then 2 in the fourth. Now, I know this isn't correct, and some of you will be saying, oh, what about 2, 8, 18? Well, we'll save that for A level, okay? But for now, we'll stick to 2, 8, 8, 2. But we need to know the limitations of that model as well in A level. So just to fix this, I've got 2 electrons in the first shell, but I need 3 electrons because I've got 3 protons, and I can't just do this. Normally, electrons are represented with crosses or dots, so I can't just do this to put a third electron in. So what I have to do is this has to go into the second shell. So this is the outermost shell, sometimes called the valence shell. Therefore, this is the valence electron, the electron in the outermost shell. Okay, I think we did that just under 20 minutes.
Now for the second part of topic 1 on the periodic table, starting with the modern periodic table, the one that you'll be provided in all of your exams. The elements are arranged in order of increasing atomic number, which we know is the number of protons. And they are arranged in columns, so that's vertical, and we call those groups. And they're arranged in those columns with other elements with similar properties. These similar properties repeat at regular intervals, aka they repeat periodically, hence why this is called the periodic table. Now, how do we link electron configuration to the periodic table? Well, the group number, again, those are the vertical columns. That tells us the number of electrons in the outer shell of that atom. And the period number, those are the rows, horizontal rows, those tell us the number of occupied shells. So for example, if we were going to look at the periodic table, and I'll take sodium as an example, seeing as I'm already pointing at it, sodium is in group 1, which tells us that it has 1 electron on its outer shell or in its outer shell. And it is in row or period 3. Okay, even though it looks like 2, the first row is actually the one with hydrogen and helium. And then the second row or period is the one with lithium, third with sodium. So that tells us that there are 3 occupied shells. Now we can also go the other way. So if we're starting with the electron arrangement, let's say we have got calcium, and we know that calcium has got an atomic number of 20, which means that its electron configuration is going to be 2, 8, 8, 2. From this electron configuration, we can see it has 2 electrons on its outer shell, so it would be in group 2 of the periodic table, which luckily matches up, and it has 4 occupied shells, telling us that it would be in period 4, aka the 4th row down, 1, 2, 3, 4. Wonderful, exactly as it should be. Now, looking at the development of the periodic table, early periodic tables were arranged in order of increasing atomic weight. They were incomplete, so not all elements had been discovered yet, and they had some elements in the wrong groups, or sometimes more than one element in the same spot. Then Mendeleev came along and developed that periodic table further, still arranging elements by increasing atomic weight, still arranging elements in groups based on their similar properties, but he also left gaps for elements that hadn't been discovered yet and predicted the properties of those elements. Now, unlike the earlier periodic tables that had some elements in the wrong groups, Mendeleev swapped the orders of some elements to make sure that elements with similar properties were in the correct groups. For example, with iodine and tellurium, iodine was actually placed after tellurium, even though it has a lower atomic weight, because it's still matched with the properties of the other elements within that group. Further to Mendeleev's periodic table, once we had knowledge of isotopes, which we saw earlier in the atomic structure section, that explained why atomic weight was not an appropriate way to order elements, as some atoms of elements have got different masses. We can summarize that here, looking at the differences between Mendeleev's periodic table and our modern periodic table. Mendeleev ordered by increasing atomic weight, modern periodic table by increasing atomic number. Both were grouped based on similar properties. Mendeleev had gaps in his periodic table for undiscovered elements, and the gaps have now been filled. Moving on to metals and non-metals, we can see that the metals are found on the left-hand side of the periodic table. And because of their electron arrangements, metals lose electrons to form positive ions. For example, if we were to take, let's take magnesium. Magnesium has got the electron configuration 2, 8, 2, as it has 12 protons and therefore 12 electrons in the neutral atom. with those 2 electrons on the outer shell. To obtain a full or empty and therefore stable outer shell, it's going to lose those 2 electrons. And so we would end up with a 2+ ion, as we've got 2 fewer electrons than protons. In terms of the physical properties of metals, metals are typically shiny, have high melting and boiling points, high densities, they are electrical and thermal conductors, they are ductile and malleable, so they can be stretched into wires and beaten into sheets. Going to our non-metals, it's the opposite. They're found on the right-hand side of the periodic table. They gain electrons to form negative ions. So, for example, if we take fluorine, fluorine has got the electron configuration 2, 7, 7 electrons in its outer shell. So in order to achieve a full outer shell, it's going to have to gain 1 electron to bring it up to 8. And that would give us a negative ion, 1-, because we've now got an extra negative electron. In terms of the physical properties, they're just the opposite. So they are dull, have low melting and boiling points, typically low density, typically electrical and thermal insulators, and typically brittle. So they are not flexible, they will snap quite easily. Going into our groups to focus on, starting with group 0. Group 0, sometimes called group 8, also known as the noble gases. These elements are unreactive as their atoms already have a full outer shell, which means they'll exist as individual atoms as they don't need to lose electrons, gain electrons, or share electrons to achieve that full outer shell and be stable. Their outer shell is full already. Looking at their trends in their boiling points, as we go down group 0, the boiling points increase. That's because we've got increased relative atomic mass, or AR. Therefore, there are stronger forces between the atoms, and so more energy is required to overcome those forces and turn those substances from liquids to gases. The next group that we focus on in detail is group 1, the alkali metals. As they're in group 1, they have 1 electron in their outer shell. In terms of their physical properties, they are quite soft. They are low density metals, which means that they float on water. And they have relatively low melting points, so that's compared to other metals. They're still solid at room temperature, but lower melting points than your transition metals, which we see in the triple science section. In terms of some of their key reactions, they will react with oxygen, with water, and with chlorine as some examples. For their reactions with oxygen, the metal plus oxygen produces a metal oxide. So for example, if we chose sodium plus oxygen is going to give us the metal oxide, sodium oxide. For the reactions with water, the metal reacts with water to produce a metal hydroxide and hydrogen. So for example, if we were to choose potassium plus water produces potassium hydroxide plus hydrogen, and that's hydrogen gas, of course, so it will exist as H2. And then reactions with chlorine, the metal plus chlorine will give us our metal chloride. So if we were to choose lithium, for example, lithium plus chlorine will produce lithium chloride. Looking further into the reactivity of our group 1 metals, specifically the trend in reactivity, the reactivity increases as we go down the group, and that's because group 1 metals react by losing their outer electron. 1 electron in their outer shell, they're going to lose that to achieve a full and therefore stable electron configuration. So how does that relate to the reactivity trend? Well, as we go down the group, that outer electron or that outer shell is further from the nucleus in the middle, the positive nucleus. That means that the attraction between the positive nucleus and the outer electron is weaker, and as a result, it's going to be easier, right, to lose that electron. That electron can be lost more readily. We see that in practice when we look at the reactions of group 1 metals with water. As we already established, that gives us the metal hydroxide and hydrogen gas. So we can see that hydrogen gas in the terms of the bubbles that are produced, and the metal hydroxide would turn the solution alkaline. So if we were to add universal indicator, then that universal indicator would turn blue/purple. Now we can observe the trend in reactivity by observations, by how vigorous their reactions are with water. So for lithium, the least reactive, the metal is going to move slowly on the surface of the water, and we're going to see gentle fizzing/gentle bubbling, or we can use my favorite term, effervescence, which just means fizzing or bubbling. For sodium, more reactive, we are going to see the metal move more quickly over the surface. We're going to see more rapid fizzing or bubbling or effervescence, and the metal is going to melt into a ball, as this is an exothermic reaction, and so the heat energy released is enough to melt the metal into a ball. And then when we move over to potassium, the metal moves rapidly on the surface. We're going to see vigorous fizzing. The metal will melt into a ball, and we are going to see a lilac flame. Okay. With the sodium, we sometimes might see a yellow flame, but that really depends on the size of the piece of sodium that you are using. The last main group that we look at is group 7, also known as the halogens. As they're in group 7, they have, of course, 7 electrons in their outer shell. Each of these elements exists as diatomic molecules, which means that they go around in pairs. So when we're talking about fluorine or chlorine or bromine or iodine, and we wanted to write the formula, we'd write those as F2Cl2, Br2, and I2, because they exist as pairs of molecules covalently bonded together. In terms of their appearances at room temperature, the key point to focus on is their state at room temperature. Fluorine and chlorine are both gases at room temperature. Bromine is a liquid at room temperature, and iodine is a solid at room temperature. Now, this shows us quite clearly that the boiling point must increase as we go down the group. Why does the boiling point increase? Well, similar to our group 0 chemistry, as we have increased relative molecular masses down the group, aka increased MR, we are going to have stronger forces between molecules, aka stronger intermolecular forces, and therefore more energy is going to be required to overcome these forces. We can also look at the trend down group 7 and predict what we would expect for astatine just below iodine. So astatine being in the same group, we would expect to also exist as diatomic molecules, so At2. And then in terms of its appearance at room temperature, well, we can see that the color is getting darker as we go down the group, yellow to green to orange to gray. We might expect that astatine would be black. And looking at the states from gas to liquid to solid, so we would expect that astatine was a solid as well, with an even higher boiling point than iodine. Looking at the reactivity of group 7 is the opposite to the reactivity of group 1, because unlike group 1 elements that need to lose electrons in reactions, group 7 elements need to gain an electron during chemical reactions. They have 7 electrons in their outer shell, which means that they need one. Oh, can I spell? They need one more electron. So the reactivity of our group 7 elements decreases as we go down the group, because as the outer shell is further from the nucleus, there is going to be a weaker attraction between the nucleus and the electron being gained. Okay, so just like group 1, outer shell is further from the nucleus and there's a weaker attraction between the nucleus and the outer shell. But this time, because we need to attract an electron in, the further from the positive nucleus that is, the harder it's going to be to attract that electron. So the atom, as we go down the group, can gain an electron less easily or less readily. It's going to be much harder to attract that negative electron if it's further from the nucleus. Now, looking at some displacement reactions, so these are key reactions of halogens where a more reactive halogen can displace a less reactive halogen from its compound. So, for example, if we had chlorine reacting with sodium bromide, which is our compound, then because the chlorine is more reactive than the bromine, we are going to have the chlorine displace or replace the bromide from its compound. So our products are going to be sodium chloride plus bromine. We've kicked the bromine out and replaced it or displaced it using the chlorine. Now, if we look at our next example, iodine with potassium chloride, iodine is less reactive than chlorine because it's further down the group, which means that iodine will not be able to displace the chlorine from its compound because iodine is less reactive. We can see this in practice with an experiment, right, where we have our halogens, chlorine, bromine, and iodine, and we place those in our spotting tile. And then we add the compound, sodium chloride, sodium bromide, and sodium iodide, and we observe whether a reaction takes place by whether or not there is a color change. If there is a color change, that means that the reaction has happened. We can predict which ones of these would take place based on our understanding of the trends in reactivity. Now, we can straight away ignore the ones where it's the same halogen, so chlorine and sodium chloride. We won't even bother to do that experiment. Bromine with sodium bromide, we won't bother to do that one. Iodine with sodium iodide, we wouldn't bother to do that one. But then we can predict where we've got our pairs. So, for example, if we've got chlorine reacting with sodium bromide, as we already established, we will get a displacement reaction because the chlorine is more reactive than the bromine, so can kick it out of its compound. And then same here, chlorine is more reactive than the iodine, so we'll be able to kick the iodine out of the compound. Moving across to the bromine, if we react bromine with sodium chloride, bromine is less reactive than chlorine, so is not going to be able to kick the chlorine out of its compound. But bromine is more reactive than iodine, so will be able to kick the iodine out of its compound. And now finally with the iodine is the least reactive of the three, so it will not be able to kick out the chlorine from the sodium chloride and will not be able to kick out the bromine from the sodium bromide. Finally, for my triple scientists and our transition metals we find in the middle of the periodic table here. Transition metals have got ions with different charges. So for example, we might have iron 2+ and iron 3+. They will form colored compounds. For example, our copper sulfate, which we know is blue when it's hydrated. And I'm going to put my water of crystallization. And they are useful as catalysts, which we see in the Haber process as an example, and also in our catalytic converters later on. Now, if we were to compare that to our group 1 metals, we can see that transition metals typically have higher melting points than group 1. They are typically stronger than group 1 metals. They are harder than group 1 metals. They are less reactive. They form ions with different charges, as we saw before, whereas group 1 metals only form ions with 1+ charges, than being in group 1. Transition metals form colored compounds, whereas group 1 metals will form white compounds if they're solids, so white solids or colorless solutions. And that is it for your periodic table. If you found this useful, make sure to hit that subscribe button, as we'll be doing the rest of the topics as well, uploaded very soon. Just another reminder, visit my resources for free revision notes, free explainer videos, free practice questions with solutions, and even examiner tips, all for free. Yes, you heard it right, completely free. Click the link in the description below and let's get cracking. If you want extra help, sign up to our courses, link in description, for weekly live lessons with us, targeted homework, video solutions for the homework, and even workbooks. Just what you need to give you the extra boost for your exams. Thanks for watching. See you guys in the next one.